Good morning. I'll continue the discussion on gas turbine cycle analysis and jet propulsion. Contents of the lecture are gas turbine cycle analysis. Here I'll discuss fuel air ratio and cycle efficiency. Then I'll learn to jet propulsion. And here I'll restrict to turboprop engine and turbojet engine. Today I'll discuss on intake and compressor and turbine performance. I'll describe now how to evaluate fuel air ratio and thus the cycle efficiency. The performance of a real gas turbine cycle can be expressed in terms of the specific fuel consumption, and the specific fuel consumption can be denoted by SFC. Thus, the specific fuel consumption is the fuel mass flow rate per unit power output of the cycle, that is, fuel consumed per specific power output of the cycle. Now I'll show you how to evaluate fuel air ratio for the cycle. Note that the T02, which is the temperature at the inlet to the combustion chamber, is assessed, while T03, that is the maximum temperature of the cycle, is normally be specified. That is what I like to say here, that T02 will have to assess and T03 is given, which is the maximum temperature of the cycle for any cycle analysis. Thus, the problem is therefore to evaluate fuel air ratio F required to perform unit mass of air at T02 to produce the temperature at T03. So I have stated here what to be done to evaluate F. Now let us consider the combustion process is adiabatic and there is no work transfer. Let me consider now the energy equation in a combustion process where del H be the enthalpy of reaction as 25 degrees Celsius, F be the fuel air ratio. For the gas turbine calculation, del H may be considered as minus 43,000 kilojoule per kg. So thus I have written the energy equation for combustion process, where for a given combination of T02 and T03, fuel air ratio small f can be evaluated. Once the fuel air ratio is known, the fuel consumption for the cycle MF can be evaluated as MF is equal to MA into F, where MA is the air mass flow. Now, MF unit would be kg per second. Thus, the specific fuel consumption can be evaluated as SFC is equal to F divided by Wn. Wn is the specific power output of the cycle. Thus, the unit would be kg per kilowatt second. Generally, the specific fuel consumption is expressed in a unit of kg per kilowatt hour. Thus, specific fuel consumption is expressed as SFC is equal to 3600 F divided by Wn, and the unit would be kg per kilowatt hour. Thus, the cycle efficiency may be defined as eta is equal to Wn divided by F into Q net, where Wn is the specific power output, F is the fuel air ratio, and Q net is sensibly equal in magnitude but opposite in sign to the enthalpy of reaction. The value of Q net is considered here 43,100 kilojoule per kg. Furthermore, the efficiency can be expressed in terms of specific fuel consumption. Thus, eta equal to 3600 divided by SFC into Q net. Now I'll discuss about jet propulsion. Atmospheric jet can be classified as air-breathing engines and non-air-breathing engines. Air-breathing engines use atmospheric air for oxygen. Examples are turboprop and turbojet engines. Non-air-breathing engines carry oxygen supply. They are commonly called as rockets, and there are two kinds of engines, such as the liquid propellant and the solid propellant. Here I restrict to air-breathing engines, that's turboprop and turbojets. I have illustrated here in brief the operation of a turboprop engines. Figure 12 illustrates the schematic of the engine. Now look here, within the core region it's having a gas turbine engine. So that is a compressor, combustion chamber followed by a turbine. Compressed gas is being extended in the turbine that produces the work which drives the compressor and the propeller. And the main propulsive thrust the engine gets from the propeller. Thus, in brief, I have written here, in a turboprop engine, the turbine drives the compressor and the propeller, which creates thrust. The propeller runs at a slower speed than that of the turbine, and thus a reduction gearing unit is introduced to step down the rotational speed for the propeller. Furthermore, the propeller deals with a considerably high mass flow rate, while the change in velocity or the pressure gradient across the propeller is low, which is just sufficient to maintain the flow. Furthermore, please note that at low speed, a turboprop engine has a better fuel consumption due to high propulsive efficiency. Above a flight speed of Mach number 0.6, the turboprop becomes uncompetitive due to its higher weight and high frontal area. In addition, the high tip speed associated with high tip relative Mach number of the propeller creates extreme noise. So these are the good or bad point of a turboprop engines. I'll now discuss about turbojet engine. The operation of a turbojet engine has been illustrated by the schematic figure 13, where the aircraft is flying with a uniform speed CA and CJ be the speed of the jet which is produce the thrust. Thus, the frontal part of the engine is the intake, which is represented by I, where air is being diffused and thereby the pressure increases. Now the pressure here more than the atmospheric pressure, and then the air is being sucked by the compressor where it is being further compressed. Then it's pushed to combustion chamber, and after that high pressurized and temperature gas is expanded in a turbine, and here the turbine work is just sufficient to run the compressor, and the remaining part of the compressed gas is expanded to the nozzle, producing the thrust. N represents the nozzle. Now, the here jet velocity that nozzle produces is much higher than the curved velocity CA, and CJ is the agency which creates the thrust. Furthermore, I like to add that in contrast to turboprop, turbojet deals with a relatively less mass flow rate, while the change of velocity is significantly high. Further, the turbojet engine becomes increasingly competitive with increase of Mach number. So thus, this turbojet engine is very efficient at high speed. The actual operation of a turbojet engine has been illustrated in TS diagram here by figure 14, where the state point A in the TS diagram represents the atmospheric condition, where PA is the atmospheric pressure and the temperature being TA. Now E201 represents the ram effect in the intake, where the pressure has increased from PA to P01. And 01 to 02 represents the non-isentropic compression in the compressor, where the temperature rise is represented here by del T0. And the corresponding isentropic compression is indicated by the dotted line here, which is 01 to 02 dash. Now 02 to 03 represent the heat addition in the combustion chamber with a pressure loss del PB, and P03 to B04 indicates expansion in the turbine, where the temperature drop is given by del T0, and the corresponding isentropic expansion is T03 to T04 dash. Now the gas is further expanded in the propelling nozzle, which is represented by 04 to 5, where 5 at the state point 5, the pressure being the atmospheric pressure PA. So P5 here is equal to PA. And 5 dash indicate the state point where the isentropic expansion. So 04 to 5 dash is the corresponding isentropic expansion in the propelling nozzle. Thus, the process 4-5 here is the expansion of gas in the propelling nozzle, producing the thrust of the engine. Thus, in a turbojet engine, the turbine produces just sufficient work to drive the compressor, and the remaining part of the compressed gas is expanded through the propelling nozzle to produce thrust. Further, the significant effect of forward speed of an aircraft demand a proper design of the intake to diffuse air, developing a uniform flow before the entry of the compressor. With respect to intake, the intake design is very critical for the aircraft with respect to its efficiency and the safety. The primary requirement of the intake design is to minimize the pressure loss in the duct, ensuring that the flow enters the compressor with a uniform pressure and the velocity at all flight conditions. The schematic of a state 2 and S-bend intake has been illustrated in figure 15. Now, S-bend intake often produce a flow distortions before the compressor, which is not desirable at all. Thus, I have given information here stating that the non-uniformity or distortion of flow may cause compressor surge, which can result in either engine flame out or severe mechanical damage due to blade vibration induced by unsteady aerodynamic effect. Further, at a normal forward speed, CA, where CA is considered as subsonic, the intake performs as a diffuser with air decelerating from CA to C1 and the static pressure raising from PA to P1. Now the pressure rise P01 minus PA is referred as ram pressure. Further, at a supersonic speed, pressure rise occurs across shock waves at intake, followed by that due to subsonic diffusions in the remaining part of the duct. Flow through the intake has been illustrated in TS diagram here by figure 15. Here is the figure 15, where I have also indicated the intake where the speed of air is diffused from CA to C1. Section AA, which represents the entry to the intake, and section 11 just before to the compressor. Thus, the air is diffused in the intake and thereby the pressure increases, which is called the ram effect. Now, I'll illustrate the ram effect here in the TS diagram, indicating also the intake loss. Before that, let me define the intake efficiency. The intake efficiency can normally be expressed as the isentropic efficiency heat high, defined in terms of temperature rise, or the ram efficiency heat R defined in terms of the pressure rise. Now, as I have told, at the section AA, which represents the NT to the intake, the temperature and the pressure will be TA and PA, along with the velocity CA. Now in the TS diagram, I have indicated the state point A, where the pressure is PA and temperature is TA. Now A201 indicates the ram effect, which is non-isentropic compression, and at 01 the pressure is P01 and the temperature is T01. Now difference of temperature between T01 and TA is nothing but Ca squared by twice Cp. Thus, I like to say here that T01 is equal to T0A, and difference between T01 and TA is equal to Ca squared by twice Cp. Thus, I have indicated the state point 01 along with the pressure and temperature. So the actual diffusions of air has been indicated here by the form line, and the corresponding isentropic diffusions is A201 dash, where temperature is T01 dash. Thus, at the point 01 dash, the temperature is T01 dash and the pressure is P01. Thus, I can say here that T01 dash is the temperature which would have been reached after an isentropic ram compression to P01. Thus, if I equate T01 is equal to T0A, I can identify the state point 0A and thus P01. Therefore, P0A minus P01 is the loss in this diffusion process. Now, that is the total pressure loss actually. Now, from 01, how can I identify the static pressure corresponding to the point 01? So, the state point 01 is associated with the velocity c1. Now, thus, if I subtract from T01 the quantity C1 squared divided by twice Cp, I'll get T1. Thus, I have identified the state point 1 and the pressure P1. So, because of this actual compression, actual diffusions in the intake, the static pressure would be P1 just before the entry to the compressor, and the P1 will represent the static pressure and T1 will represent the static temperature, while P01 represents the total pressure and T01 represents the total temperature. With this, one can appreciate the ram effect and thereby the pressure loss in the intake. After explanation of flow through the intake in TS diagram, now I can establish the equation for the intake as T01 is equal to T0A is equal to TA plus CA square divided by twice Cp, and P01 divided by PA is equal to T01 dash by TA to the power gamma divided by gamma minus 1, where 01 dash is the isentropic state point and 01 is the actual state point, that is actual condition after diffusion of air in the intake. Further, T01 dash can be related to T01 by introducing the isentropic efficiency eta I of the intake, such as eta I is equal to T01 dash minus TA divided by T01 minus TA, referring to this figure, which yields the following relation as T01 dash minus TA is equal to eta I into Ca squared divided by twice Cp. Thus, eta I can be regarded as a fraction of inlet dynamic temperature, which is made available for isentropic compression in the intake. Thus, I like to state further that eta I can be regarded as a fraction of inlet dynamic temperature, which is made available for isentropic compression in the intake. Now, we can relate between P01 and PA, which defines the ram pressure. Thus, the intake pressure ratio can be found out as P01 divided by PA is equal to, within bracket, 1 plus T01 dash minus TA divided by TA to the power gamma by gamma minus 1 is equal to 1 plus eta I into Ca squared divided by twice Cp into Ta to the power gamma by gamma minus 1. Thus, if we know Ca, which is the craft speed, and atmospheric condition, that is Ta, considering eta I, which is the efficiency of the intake, we can define the ratio of P01 by PA. Furthermore, we know the relation, that is Mach number M equivalent to C divided by root over gamma RT, considering the ideal gas, and also gamma R is equal to Cp into gamma minus 1. Thus, using these two relations, I can establish P01 by PA is equal to 1 plus eta I gamma minus 1 divided by 2 into Ma squared to the power gamma divided by gamma minus 1. So here P01 by PA has been related to Mach number of the craft. Furthermore, the stagnation temperature can also be related to Ma. Ma is the Mach number of the craft, as T01 by Ta is equal to 1 plus gamma minus 1 by 2 into Ma squared. Now, the ram efficiency eta R is defined by the ratio of ram pressurized to the inlet dynamic head. Thus, eta R is equal to P01 minus PA divided by P0A minus PA. Further, the ram efficiency eta R can be shown to be identical to the isentropic efficiency eta I, and the two quantities are interchangeable. Now we'll move to compressor and turbine. I have already explained that in a turbojet engine, the turbine produces just sufficient work to drive the compressor, and the remaining part of the gas is expanded through the propelling nozzle to produce thrust. So I'll explain now non-isentropic, or the actual compression and expansion process in the compression and turbine respectively. Flow through the compressor has been illustrated in TS diagram, where 01 to 02 is the actual compression, which is indicated by the form line where entropy has increased, and the corresponding isentropic compression is represented by 01 to 02 dash. Thus, the isentropic efficiency of the compressor can be defined as eta C equal to isentropic work divided by actual work. Now, in a compressor, actual work absorption will be more than that of the isentropic work. So that eta C can be equated as actual enthalpy rise with respect to isentropic enthalpy rise. So I can write 802 dash minus 801 isentropic enthalpy divided by actual enthalpy 802 minus 801. That is equal to, if we consider Cp remains constant, not a function of temperature, then T02 dash minus T01 divided by T02 minus T01. Thus, isentropic efficiency of a compressor is equal to the ratio of isentropic temperature rise by actual temperature rise. Furthermore, the pressure ratio can be related as P02 divided by P01 is equal to T02 dash by T01 to the power gamma by gamma minus 1. Now for the compressor, I can write T02 minus T01 is equal to T01 divided by eta C within the bracket P02 by P01 to the power gamma minus 1 by gamma minus 1. So this you will get if you combine this relation with the definition of eta C. So this is the relation which tells us the actual temperature rise with respect to the inlet temperature, eta C, and pressure ratio. Similarly, I can define the isentropic efficiency of a turbine. Thus, flow through the turbine has been illustrated here in TS diagram, where 03 to 04 dash represents the actual expansion where entropy has increased, and 03 to 04 dash indicates the isentropic expansion. You can appreciate here that actual work is less than the isentropic work. Therefore, the isentropic efficiency for a turbine I can define now, eta T is equal to the actual work divided by isentropic work. That could be related to 803 minus 804 divided by 803 minus 804 dash, H being the enthalpy. And if Cp I can assume as constant, then this can be related with the temperature drop, T03 minus T04, actual temperature drop, divided by T03 minus T04 dash, that is the isentropic temperature drop. Further, using the isentropic relation, I can write P03 divided by P04 is equal to T03 divided by T04 dash to the power gamma by gamma minus 1. So this tells you the pressure ratio. P03 by P04 is equal to T03 by T04 dash to the power gamma by gamma minus 1. Now if I combine these two relations, I'll land to the expression of T03 minus T04, that is actual temperature drop, is equal to eta T into T03 within the bracket 1. Again within the bracket 1 divided by P03 by P04 to the power gamma minus 1 by gamma. Furthermore, I like to tell you that eta T tends to increase and eta C tends to decrease with the increase of pressure ratio for which a compressor or turbine are designed. Thank you for listening.